tornadoes may be super destructive, hail and hurricanes are super destructive, but they don't happen every day, right? So you train up on a database of 30 years of data, if you can have a database of 30 years of data, but now you have a distribution that's actually shifting, because in those 30 years, things have actually observably changed. And so you have to take that into account when you're giving it into your AI data. Let's stick with a hurricane example, the rapid intensification, how much it's going to intensify in 24 hours. In the last few years, that has really changed because the ocean is warmer. And so our models, if they were trained on the last 30, 40 years of data, might not be doing a great job of predicting that. So we need to be aware of that so that we're actually training the models on the more recent data so that we can create a model that is more trustworthy and also more likely to be correct about whatever the next storm is. My ultimate goal is that we have made ourselves more resilient to climate change by understanding all of these phenomena better.
AI2S is all about trying to build trustworthy models about weather and climate based on the information that we have available from a whole variety of different kinds of sensors.
So we're an NSF-funded AI institute that is creating AI for a variety of weather and climate applications. We are creating AI that will actually be used in a variety of high-risk situations, so life and death situations like tornadoes and hurricanes, and as well as longer-term things. But creating AI that will actually be trusted, not just AI that's in a lab that you say, oh, this looks good. We want to make something that actually saves lives and property.
The machine learning side of things is trying to automatically construct and evaluate those models based on historical data that we have in such a way that we have a better feel for how it applies to the future and a better feel for how we should be communicating that information.
We are trying to give the best information that we can to people to protect themselves and their property. And we do that as humans by interpreting a lot of data and making decisions based on that data.
Models need labelers. Models need human interaction to continue to grow and evolve with our thinking. So as the data becomes more sophisticated or the model becomes more sophisticated, to know if we're doing well or doing better or improving, we need people. We need people to bounce that information off of. We need interaction. It's that interaction that is the magic of AI.
We really want to start to understand in detail the relationships between lots of different variables that we can assess. So that we've got the images coming into the mesonet sites. We have other sensors that talk about precipitation, that talk about temperature, wind direction, and speed, etc. There are also other kinds of things that are being sensed, say, via radar or satellite, and we'd like to be able to bring all of that information together into one comprehensive model. So that really requires us to start to understand the statistical relationships between these different kinds of variables.
One thing that we can do is learn a lot from what has happened already in the atmosphere and how certain changes relate to those climate signals in our system. And that may allow us to then project what could be happening in the future in finer detail. I mean, storms are an excellent example because our climate models do not explicitly predict storms. They predict some prevailing changes in the large-scale environment. And we have to use our intuition and our known understanding of these relationships to consider what could happen in the future.
An interesting question is, okay, now that we're bringing in these different computer science methods that have been out there for so long, like co-training, self-learning, and so on, additional computer vision methods that may have to do with data augmentation techniques and may help us, deal with class imbalance. Ultimately, we would also like to be able to give better explanations as to what kind of predictions we actually make, and try to provide models that are either interpretable by themselves, fairly interpretable, or provide methods that really create some kind of feedback mechanism and say, okay, yes, we made this kind of prediction, and really our decision is based on such and such kind of observation.
Visibility is a very important meteorological variable. It's often used, I think, mostly with like airports or any sort of like automotive traffic. So, right, visibility is things like fog or smoke, anything that impedes line of sight to the horizon. And so the way visibility is currently being detected at like airports or other sites is using sensors. And they can be kind of expensive, they're very specific, they can be hard to deploy, you have to calibrate them and stuff like that. But something like camera images is highly available, accessible, right? Roadways and highways have tons of cameras lining them, monitoring the road conditions. So if we could detect visibility from just camera images, that would be really cool and awesome. We can detect visibility across the state of New York, or at least the roadways of New York. And how that kind of works is, our thought process behind it is, if we have a large enough sample of images at a particular site, you can see the historical data of like fog rolling in and out of the site. So you can get a sense of what the site is composed of, what it looks like with low visibility, what it looks like with high visibility. And so from the camera image, maybe you can get a good estimate of what the visibility is. Or at the very least, you can detect whether visibility is dropping or you have clear visibility for the site. But visibility in terms of like automotive traffic is also very important for things like self-driving cars, right? If you have a self-driving car that usually relies on visual cues in the environment, what happens when those visual cues decrease? Can we detect when visibility is very low, and does that change the system?
The neural networks that we use follow along a similar kind of idea. They're very simple individual computing elements that take in a bit of information, they make a decision and then pass that on, typically to a separate set of neurons, and they do their computation and then they pass that on to another set of neurons. And very often, as we go from one layer to the next, our representations are getting more and more abstract. So as an input image is coming in, the next layer up will start to summarize key aspects of that image. Where are the trees in the image? Where are the mountains in the background? And then the next step can start to assess, say, how easy it is to see each of those features in the image. And ultimately we end up with an estimate of visibility that is possible through the atmosphere in that image.
To some extent, there is a big human component when you're assessing when you deploy these models and who you're deploying them to, and even who the end user is going to be, because you don't want your machine learning model to give information to people that will cause them to make poor decisions.
We need to demonstrate that there are known and well understood physical reasons that the model takes this data and gives this answer. What is it finding in this data that's telling it this storm should be severe?
There's the numerical weather models that are being produced, and there's all the different models that are being produced. The United States and Europe are producing different kinds of models. There's all the sensing systems that are out there. Some of them are producing data every 30 seconds. The humans can't deal with all of that. So if you're talking about real-time forecasting, then it's really, really important that we can do something that can help you make sense of all of this data and help you just sort of focus in on, okay, this is the area I need to look at. The lead time has gone up to an average of 15 minutes, but 80% of the time you're calling a warning, it's false. Now, they're warning over 80% of the tornadoes that happen, so that's great. But 80% of the time that you call a warning, it's false. So we'd really like to be able to bring that down, for example. And the way to do that with the current systems that exist, there isn't really any additional sensing systems we can bring online that will actually tell us what we need. What we need is to use AI to sift through all of the data that exists already and try to find other kinds of patterns that could be used to improve our predictions.
I think what we're doing is good, and in the end, a lot of the applications that come out of AI 2ES, I think, do save lives in terms of communicating information to people when they need it or before they need it in order to make life-saving decisions.
The hope in making this, at least in part, a data-driven endeavor is that we can start to do a better job of modeling these phenomena, and hopefully also turn around and give the practitioners a bit more insight into the physics of the situations that they're looking at.
I personally am trying to do good for humanity because I want to make the world a better place than where I started. And the way I'm trying to do that is to help make all sorts of interesting AI applications that will help save lives, save property. The way I'm doing that at the moment is through AI2ES, right? Helped create this giant team of people who are really passionate about trying to help improve our climate resilience, help to create AI products that will actually solve interesting problems. And so I would say that I am doing good, and also AI2ES is doing good for society.